Welcome back, guys. Today we are going to be looking at coming up with notation for this inverse that we were doing yesterday. So yesterday we were looking at exponential functions. For example, let's say f of x is equal to 2 to the x, right? And we were doing things like, what is f inverse of 1 over 16? Well, 2 to the what power equals 1 over 16. That's going to be negative 4, right? Because 2 to the negative 4th equals 1 over 16. This inverse is spitting out this exponent, right? Or if I did another example, say f inverse of 8, what is that going to be equal to? Well, it's going to be equal to 3, right? Because 2 to the third equals 8. Now this notation is kind of cumbersome because I have to give you like an original function, the original exponent, so that you can figure out what these f inverses are. Without that original function, tell me what part wouldn't you be able to do in trying to evaluate something like f inverse of 8 is 3? If I kind of ignored that, what do you need to know in order to be able to go from 8 to 3? It's not just a straight up, let's multiply and add and subtract. It's not one of these typical types of operations that we use for functions. We're not squaring anything, right? Whatever operation you would try and find to go from 8 to 3, you couldn't use that same operation to go from 1/16 to negative 4, right? There's got to be something else that we can use. Well, a long time ago, they developed a different notation for this type of an inverse function. It was a logarithm, and they could write, for example, I could rewrite this inverse here as a log of 1/16 is equal to negative 4. But in order to tell you that we're using the exponential with a base of 2, the log, we would normally write a little subscript down here to indicate the base of the exponential that we're using. So we would say log base 2 of 1 over 16 is negative 4, because 2 raised to the negative 4th is equal to 1 over 16. This log, just like our inverse, always equals the exponent, right? And it's the exponent relative to the base, which is your subscript here. So in general, all exponential statements, things like base raised to a power, let's call that a, equals c, can then be written in an equivalent logarithmic format where we write log, our subscript is our base, c equals the exponent a, right? Sometimes I've seen people say log base b of c equals a, and they do this kind of circle the base and do an arc with it because it works both ways. Log base b of c equals a, I can rearrange this log doing log base or b to the a equals c. Like rewriting that as an exponent kind of uses this same exact curve, b to the a equals c. Log base b of c equals a, and we can use this to rewrite from one form to another. So if I had to rewrite an exponential in log form, we could do that for something like 5 to the third power equals 125. That would be rewritten as log base 5 of 125 equals 3. Base goes as a subscript. It always equals the exponent. And then what is it? 125 is inside, right? Because 5 to the third equals 125. And there we have it. Also, we can rewrite logs in exponential form. So if I gave you a log statement, let's say a statement like log base 7 of 1 over 49 is equal to negative 2. Well, that could be written as 7, the negative 2, what the log equals, that's my exponent. 7 to the negative 2 is equal to 1 over 49. And there we have this log type form. So let me give you a trial, right? Try and write down 2 to the negative 4/7 equals 1 over the 7th root of 16. Rewrite that into log form. So log, what's the base going to be equal to? Good, that's 2. What is the whole log going to be equal to, right? Log base 2 of something equals what? What does that log spit out over here? Good. Negative 4/7, the exponent. The exponent is what the log equals. And then, of course, in the last spot inside is 1 over the 7th root of 16. Good. All right. Now, anytime I ask a student to evaluate a log and they tell me, oh, I don't know how to do logs. Logs are so difficult. I don't know. And I understand. It's very, very odd. We're now using a function. We have no idea what operations are going on, but we set up equations. 2 to the what power equals 1 over the 7th root of 16 and so on, right? That we think about solving that equation, or we actually do. But if a student says, you know, I have no idea how to evaluate log base 27 1 over the square root of 3. No idea how to do it. Well, I say change it to an exponential and solve it. I mean, we know how to deal with exponents. So what is this log as an exponent? What is it saying? It's saying 27 to the something equals 1 over the square root of 3. And the log is going to equal that exponent, whatever that something is. Now we have an exponential equation. I can just rewrite that box as x, and we can go through and solve it like we've solved so many others before. Give me a common base between 27 and 3. Well, 3. 3 to the 3rd is equal to 27. And what's 1 over the square root of 3? That's 3 to the negative 1/2. Set the exponents equal, right? Because if the base is the same, the exponents have to be equal. We get 3x equals negative 1/2. X is going to be equal to negative 1/6. So log base 27, 1 over the square root of 3 is equal to negative 1/6. And there you're done. Anytime you can't solve a log, change it to an exponential and solve it that way. Makes it much easier, and it makes it this new problem look like an old problem. Right? Great. Thank you.